It's a great pleasure to be here in Marrakesh, and I would like to thank both Dr. Saidi and Yusuf Zaz for inviting me and to give me the opportunity to participate in the conference as well as to be in Marrakesh. And in Morocco. It's my first visit, but I'm sure it will not be my last. It's a beautiful country, and I'm happy to be here. So without further ado, let me start the talk. I'm going to assume that not all of you do know what archaeology is, so I'm going to kind of introduce you to it. So what is archaeology? It is the beeping tom of the sciences, basically. I don't know how many of you do know what the beeping tom is, but I'm not going to further explain. And it is the science where one learns more from the dead than from the living. This is what archaeology is. I'm making a joke, of course, but and why archaeology? The first one is, until lions have their historian, tales of the hunt always glorify the hunter. This will be like something like the late Edward Said would say in terms of who writes history. Is it the hunter or the huntees kind of thing? 500 years before Christ, Confucius would have said, I'm not the one who's born with the possession of knowledge, but I'm fond of antiquity and therefore I learn through it. So the million-dollar question is, what is a electrical and computer engineer or a computer scientist do in archaeology? And basically, do you know that guy? That's Hawaz. He used to be the Minister of Antiquity in Egypt during the Mubarak regime, not anymore. But he's a respected archaeologist. And basically, what we do is we dabble in ruins instead of having a career in one. I don't want to have my career ruined, so I'm dabbling in it as well. And another reason is we are trying to change the epistemology.
I think we have to start. I would like first to thank you again for coming.
Because that's my cue to give them 5 minutes to talk.
We'll start the session 5.
Coming before Christ, insofar as archaeology and my talk is concerned, is before and after computer. So it becomes before computer, basically. Who are we? Quickly, we are computer vision practitioners collaborating with archaeologists to facilitate their work and to make their main task be historical interpretation of culture rather than the mundane task of mending and spending hours upon hours of taking fragments, making them into vessels, and then start the historical interpretation. This is a National Science Foundation project sponsored by NSF in the US, and the composition of the team, we have people from electrical engineering, computer science, multimedia, archaeologists, and we are collaborating with and of course the graduate students both at the graduate and undergraduate level. And we are collaborating with the US Department of Interior and the National Philadelphia Park in Philadelphia. And basically there are digs in the 18th century in Independence Hall, where the interest there is to really study slave history during the 18th century in the US. What are the overarching goals of the project? is to help in the reconstruction process, freeing the expert, as I said, from hours upon hours of mending those pieces into vessels before they start doing the historical interpretation.
Hello.
Also supplying tools for storage, for sorting and virtual spaces for learning and dissemination. One of the big obstacles that you have when you are going to a dig is that you want to really preserve the artifacts, and therefore they usually store them in place, and they are not open to other researchers away actually from the dig. Neither are they less so also from people overseas. So if you can create a media, a virtual media, whereby you can store, you can navigate, you can manipulate these objects, then it becomes amiable to people everywhere and instantaneously. So it helps more in terms of studying cultural heritage and not just dedicated to one group.
Is supervised by Professor Lej Mohsin. The title of the topic
moreover,
is about cloud computing, integration, and
immigration. Well, anybody has a problem with immigration here? No. Preserve a valuable asset in situ. So you could do, one can envision coming up with a vision system tools where you can have scanners and intelligent systems that can do the interpretation of historical interpretation on the dig themselves by scanning fragments and assemble them automatically. Good to form, since I am from academia, we always are judged by three measures: research, teaching, and services. And insofar as that is concerned, this triad, I am going to also tell you what we have done along the research line, along the teaching line, as well as the service line, the service. By and large, what is in place now in terms of what we call the classical archaeology is you go to an archaeological site, you have experts doing the dig, getting fragments, either trying to study the fragment on site or moving them to a depository or a lab where they can start mending and then studying. And what we envision, we and others, since we're not the only one doing that, is to come up with a computer vision toolbox that does digital scanning and using various modality. Could be like a 3D scanner if you want 3D coordinates, cameras, ultrasound. You can think of many different sensors that can help you in the reconstruction. You do the mending using the expert opinion to facilitate your mending process through the computer. And then you create virtual libraries where you can manipulate those, navigate, and you export them anywhere you want. So by and large, the new paradigm will be to have we, the engineers, interact with the expert in creating these tools that will facilitate their life and disseminate the information everywhere. For our project, by and large, the data collection was limited to a scanner, 3D scanner, and cameras. And you could see some of my graduate students actually and taking those parts, which are ceramics, thin ceramics parts for the dig, and scanning them, and then importing them to a computer and try to do the mending there. Now, the relevant questions, insofar as we, the technology creator, are concerned, are: what Q can we extract? If you give me those fragments and those vessels? What are the cues that will be helpful in doing the mending? That's one. And reconstructing it. Two, how is the expert opinion factored in? I cannot just have an automatic system that sideline the expert. The experts, who is the archaeologist, I need their feedback. And how do I incorporate their feedback in a dynamic process so that the expert also learns from the artifacts that they have no knowledge of, in addition to the artifacts that they have prior information on. The other question is, can we go beyond the visual? Are there features that the expert is not using, but the computer can extract and use in order to do this mending process? And what does that technology at the end of the day offer? What do they offer? Is it really a paradigm shift or just a quantum leap kind of thing? And in my mind, really, if it's put in its, if it reaches its potential, it is a paradigm shift. Because it changes totally what most of the time of the archaeologists is spent on. It is spent on cultural interpretation and heritage history, not in terms of mending those pieces. And how do we envision the future of archaeology with this technology? So these are relevant questions that one should ask and try to answer one by one. So with regard to the first one, what cues should look at? Now from the expert point of view, and also what are the cues that the expert uses to mend those artifacts into vessels. There is the obvious one, which are surface breaks. So if you think that you have a vessel that over time has been broken into pieces, how do the pieces break? And can you use the surface break to put them back together? As a child, I was interested in jigsaw puzzles, and that's maybe the equivalent or generalization of that in 3D, not in just 2D, using surface break. One can also look at marking. Are there marking on the surface that one can make use of, and looking at the continuation of that marking from piece to piece in order to mend those fragments together? Can one look at the surface information? Is it a flat surface? Is it a concave, a convex part? How does the curvature change? Can one use this information in mending as well? The texture. How rough is the surface? How does it appear? Can one use that information? And also, at least at the minimum, pruning the number of artifacts that don't belong, and then entertain the one that have the surface characteristics or texture characteristics that are consistent from piece to piece. The color, of course. If you're looking at ceramic parts, they have color in them. We should also use the color in order to do the mending. I'm from Egypt originally, so here it goes. This will be the puzzle that I would try to solve, but bear in mind, since I am in the US, what history for them is 18th century, what history for the Egyptians is 7,000 years ago, so it's very different. But nonetheless, the problems are very similar, and that is what information you should use. So let me start first with how can we use surface breaks. I'll go through one by one in order to do mending. Surface break is you use it when you have no prior information at all. So basically, the expert tells you, I am in a dig, it's completely alien to me. I don't have historical prior information about marking you should be looking for or certain surface characteristics. So by and large, you depend on the surface break of these fragments and try to mend them together. And the way we do that is, like this is an example, where you have parts we extract the outer contour of these fragments and then get fiducial points on these fragments and try to see if there are equivalent fiducial point on a different fragment, and then put them into correspondence, mend them the two together, and it becomes a big part. And then you keep on going, adding and adding and adding until you can't add any more. Or if you have a part that doesn't fit, then you stop there. So here is a simple example where you have fragments on a bin. Some belong to the same vessel, some do not. And you could see that you get the outer contour, then you get the fiducial points on them, and you try to establish correspondence quickly. This is real time, by the way. And of course, it has been scanned in 3D. I'm not including the scanning part, but since the scanning, and it says, well, this belongs to the same object, and it fits it together. And the rest, no, they don't belong to that object. So in the case we have expert opinion, which in most cases it is, I would like to incorporate that expert opinion. And how do we do this? And in what form does that expert opinion come in? Well, it can take different forms. The expert can say, well, I know during that part of the 18th century, the ceramics came from England. It had this type of patterns, and I can incorporate and look for these patterns. And these patterns will appear differently if they are projected on a plate versus a vase. So that means, although I know that there are those patterns, how it manifests itself is subject to uncertainty depending on what kind of vessels we have. We can also say, the expert can also say, well, you know, in this dig, we're looking for vases. So, but I more or less, these are the prototype, but he or she, the expert that is, are not 100% sure. So you have to build in uncertainty in that expert opinion. And the uncertainty could be in terms of computational, somebody working in computational vision is transformations. So within a transformation or a set of transformation that you are allowed, you can have a generic model that, and then there are variation on that generic model. Hence, when you're using the marking or surface information, you should go after features that are preserved under this set of transformations, and then use theory of geometric invariance and differential geometry to get to fiducial points and use these fiducial points to do correspondence with the generic model, and then you align to that generic model, which is one of many, because you have so many transformations, but it's blind to that transformation, and that's the beauty of it, that you have uncertainty built in. In terms of building the generic model, we can also help the expert by creating a GUI system or a CAD design where the expert sits in. We give him, say, okay, it's a vase. So we give the expert the vase, and then through a GUI system, he said, no, the vase should have this curvature around here. Okay, the pattern should be here, not here. So they have this, through the CAD system, the ability to manipulate the shape of the object, where the patterns are, to come up with new models to help me, the computational person, in doing the mending. So there is a give and take, and then we go back, we try to do the mending, come back to the expert, and say, well, these parts have not been aligned based on the information you're giving me. So the expert looks at a smaller subset, then go and learn a little bit and say, okay, based on what I see here, you should change the model into this or that, add a few features, and so on. So there is a dynamic interaction between we, the computational people, and the expert in tuning the generic model that we are going to use and help us in the mending process. With regard to the second one, which is vessel reconstructed from fragment using vessel marking, once we have the generic model that the experts have given us, then, which are again built, there is a variability in terms of transformations. We go and use the marking that we find on a fragment and look at equivalent one on the vessel, the generic one, and see are there places where if I take that marking and I transform it within the set of allowable transformation, will it go somewhere on the generic model? Then I map it there if it is, and I keep on doing this. And then here is an example where this is the generic model, these are fragments. And for each fragment, there are contours. I can get a representation for each of these markings through a lot of tools. One of them will be like getting the convex hull of that marking, getting the vertices, and align the vertices of the convex hull, the contour, like we have done in terms of the fiducial points. That will be exactly the same kind of concept. And you have then you say, okay, this part should be aligned to the generic model, this part should be aligned to the generic model, and you look at the overall error. And the error there is how much of an error are you getting between the coordinates of the aligned relative to the generic one. And you compute that error and you see, is it acceptable error or is it too large? And that's like a distance map, like the shortest distance. And if it is within the resolution of the scanner, then you have done a very good job. If it tells you no, relative to the resolution of the scanner is 3-4 times, then it doesn't belong. So although you find the pattern, you find the most likely placed on generic, but the error is too high, and you say that doesn't belong to that part. What happens when you have surface that doesn't have marking, but you have a priori knowledge in terms of what the expert gave you in generic model? What you do is use the differential geometry of the surface to get marking, which are extracted from the differential geometry of the surface itself, like parabolic contours, for instance, which are preserved under the set of affine transformation. And then you, on these parabolic contours, get fiducial points and use these fiducial points to drive your matching. And by the way, these are features that is definitely going beyond the visual, because an expert cannot see those parabolic contours or the differential geometry curves. An example here will be what you see, the ceramic face. And these are the parabolic contours that are preserved under the affine transformation, which means I can have this face or any piecewise affine transformation on that face, and I will still have the same representation and the same kind of alignment. Here is a case where you have two ceramic faces, one of them, or a statue, one of them, it's the same statue, but one is smiling, or not really smiling, is kind of turtle, the other one is have a smirk on their face. And using the parabolic contours and fiducial points, it was able to find correspondences. And even on the mouth, although the gesture had changed, it is within the allowable transformation, so it says, yeah, that belongs to the same statue. And then it aligns them. So you say, okay, based on this transformation, I will compute the transformation now that I have correspondences and inverse map them. And you could see the inverse mapping there. They are almost on top of each other. And if you look at the error, the computational error, it is within the resolution of the scanner, 1.6 millimeter average, and with a standard deviation of 0.75. So it does a very good job in the alignment. It tells you these two indeed do align, although they are different gestures. You can also do partial alignment. You could have maybe a part of a nose and you can go through the same dance and align it and look at the error of the alignment, and you could see also it is within the resolution of the scanner, which tells you this is a good alignment. Anybody who works in any field knows quite well that you are not it's not one feature is going to do everything for you. And the degree of success is if you fuse different features together in getting a better, or different, in biomedical would be different modality. Use ultrasound, MRI, CAT, or in here, use texture, use marking, and fuse them together and see if you can get a better alignment. And indeed, here is an example where you have different shirts, different vessels, and these are mended. Some of them are mended using marking, some of them mended using surface information, some of them are mended using breaks. And when you put them all together, you start by saying, okay, with perhaps surface breaks or marking, I'm getting 50% of them, of the fragments. But if I add to marking surface information, I'll go to 66%. I add surface breaks, I will come to 89%. And this is exactly what happens here. If I look at the mending results, in this particular case that I'm showing, there are 256 fragments. The number of fragments mended using surface marking was 57% on its own. But if I take that and add to it the mending using surface information, it goes from 57 to 66. And if I add the surface break, it goes to 89. So 89% of the fragments were totally mended into those vessels using a diffusion of these three features together. And also in terms of the remaining one, the 11% were very small fragments. You don't have any information basically. And if you look at how much of the volume was mended of these vessels is 95%. So it's even more than 89. 89 is the number of fragments, and some of them were very small, so you didn't have any information. But if you look at, in terms of the volume of the vessels, how much were you able, using this set of information, to automatically mend these features, it came to 95%. This is encouraging. Of course, this based on 256, one should try to see what happens when you have thousands and thousands of tensors. But at least in terms of feasibility, it shows that these ideas are solid, and also that the fusion of them is something you should definitely consider. So to answer the question of what this technology will help in, it definitely will help you in get remote learning, navigation, and exploration through these computer vision system tools. It helps you in dissemination and manipulation. So a lab in Morocco, in Marrakesh, instantaneously, I can send all my findings in Philadelphia to them, or in France, and they can look at exactly the same parts, either improve on the mending, or for that matter, if they are archaeologists, do historical interpretation and cultural knowledge. So the beauty of virtual reconstruction is that it's portable everywhere. With regard to teaching, we have also done quite a few things, since, as I said, there are two components, so that's the second one. We have created a new course on what's called computational archaeology, and it was open to computer scientists, engineering, people from multimedia, from archaeology. And this is something that really I'm personally proud of, because I feel like for the longest time, computer vision has been dedicated to military, definitely biomedical, but military applications. and it is nice to open it to the humanity at large. And this is a project that does that. And we have other project that looks at translation, looks at other things that we would like to develop computational tools to it. And this to me is the way to go, is to help the humanity and not just military application. So the course was ECE 690, and it had a senior undergraduate and graduate student from, as I said, from different disciplines. It was a 3-hour course, and the interesting part is that we took the student to the archaeological digs, and they had a project at the end based on data that was from there. So they learned a lot, actually, not just from the theory, but the implementation of the theory, and interacted with archaeologists and experts in that field. We also able to take these tools and make them sexy tools that could be used in schools to talk about archaeology within the context of, here, guys, you see those pieces, we play with them, we mend them together, so it's like hands-on. You get excited by seeing, instead of, well, you know, in 1921 this happened, or in the 17th century that happened. It becomes detached. Whereas if they get their hands in it, it becomes more personal, and they learn more of it. We also had a workshop at the International Conference on Computer Vision that was dedicated to computational archaeology. And it was very well attended and excited, and they had people from all over the world, expert and non-expert, who were interested in seeing what engineers and computer scientists can do by talking to engineering, and vice versa. What can we learn from them? What can we help them with? And we had people that were archaeologists as well in that conference. So that was a very nice synergy between these two groups. So in conclusion, we presented a system tool based on computational tools or computational vision that can help the archaeologist in mending. We definitely get the expert opinion. We are not eliminating the expert opinion by no means. We're not the expert, they are. And hence, having them in the loop would be useful for us as well as for them in terms of the mending process. The system, if I kind of project in the future, I could see that it could be really opening up the archaeology field. Instead of a class of people working on this, in this site, on that site, and another one on that site, it's open to everybody through the virtual reconstruction. So, with that, I will stop, and if you have any questions, please do.